Probably
Super
doesn't.
interesting. It's really fun.
All right.
It's probably not included.
Taking a look here at the Chapter 6 teamer. A storm washed away sand from a beach, causing the edge of the water to get closer to a nearby road. The rate at which the distance between the road and the edge of the water was changing during the storm is modeled by this function. So again, whenever I read the word, I'm always going to circle that. Meters per hour. T hours after the storm began. The edge of the water was 35 meters from the road when the storm began, and the storm lasted 5 hours. The derivative of f of t is f prime of t equals 1 over 2 root t minus sine t. I think we could have got that from taking our derivative. What is the distance between the road and the edge of the water at the end of the storm? So let's draw a picture maybe. Here's my road. Here's my water. It was 35. But the water is coming closer to the road at the rate of f of x, or f of t. So the storm lasted for 5 hours. So we can talk about finding the total loss by going from 0 to 5 of f of t is negative 8.505. And that'll be in meters. So we've lost 8.505. We started with 35. So make sure we include the 35 plus that. And our answer the only answer acceptable will be 26.495. And I think that's in meters. Good. Using correct units, interpret the value of f prime of 4 equals 1.07 in terms of the distance between the road and the edge of the water. So we've put in 4 into the derivative, and it is 1.07. I would also encourage you to look at, so we've got the derivative of a rate, because f is a rate. So I've got a derivative of a rate. What is the actual rate at 4? And I think that we get negative 1.653. And I think that number makes sense. So that's in meters per hour. So then this one would be in meters per hour. So what does that mean? The rate is negative. We're losing feet. We know that. We're going this way. But the rate of the rate is a positive number. So that means the rate of the decrease is increasing. Meaning the change in distance is decreasing. I think either one of those would be good answers. So it's slowing down. The rate of decrease is slowing down. That'd be a good answer. At what time during the 5-hour storm was the distance between the road and the edge of the water decreasing most rapidly? Well, we know it's not going to be at 4 because that was a positive number. But we're looking for a maximum of decrease. And this is the rate of decrease. So if we're looking for that maximum, we're going to derive that. So f prime of t, we want that to be equal to 0. So we've got our f prime that they gave us, 1 over the 2 root t. So if we graph that, we get this guy here from 0 to 5. So it's 0 here and here. And I think if I calculate those, I get 0.662, 2.840, 0. And now I've still got this rate. So we always need to check the endpoints. So we need to check 0, and we need to check 5 to see if those have a higher rate than either one of our zeros. So as I put those in and check them in the function, so just using my table, I get the rates of -2, -1.3, -2.2, and -0.48. So I can see that the distance between the road and the edge of the water was decreasing most rapidly at time 2.840. You definitely get points for checking the endpoints, so don't forget that. After the storm, a machine pumped sand back onto the beach so that the distance between the road and the edge of the water was growing again in meters per day, where P is the number of days since pumping began. Write an equation involving an integral expression whose solution would give the number of days. So I need an equation with an integral. That sand must be pumped to restore the original distance. So the original distance was 35, and we lost this 8. So a couple options here. We could set it equal to 8. I guess that would be one option. We could just write that number 8.505. And when will this equal that? And that's really kind of all we need. Here's our integral expression. We need to know when this integral, because we've got a rate, will equal to 8.05. And then we can shut off the machine pumping the sand back on. Good math.